I'm going to start for about half of it, and then Radu will take over in a little while. But this brings me back more on my schedule. So let me see, what lecture is it supposed to be? I don't know. Maybe it's lecture 5. So I'm going to talk about waveforms and scattering from amplitudes. Amplitudes. Okay, now the waveform is essentially a measure of the Riemann curvature. So classically speaking, if you go to a certain gauge, it's called transverse traceless gauge, TT gauge. Well, then the Riemann tensor is up to some factor, a second time derivative of the metric perturbation. And what a detector like LIGO measures is the projection of this metric perturbation on some polarization tensor, basically that's set up by the direction of its arms and its orientation in space. So that's the H of t that LIGO reads out, right? These wiggles. Now, in quantum field theory, we can't measure the Riemann tensor. The Riemann tensor is replaced by an operator, but what we can measure is an expectation value of the Riemann tensor. So that's the observable that I'm going to be interested in. The observable in QFT. So it's an expectation value of an operator like this, which you got to go ahead and compute, right? So I'm going to be interested in scattering, as usual, mainly because the analytic continuation, or however one would go to the bound state situation, is something that we don't really know how to do. I mean, there's certain examples where we don't know how to do it for this thing. Radu is going to discuss some examples where we do know how to do it, but it would be very interesting to learn how to connect to bound state waveforms for obvious reasons, like LIGO is a bound state, right? LIGO detects a bound state. But anyway, so what that means is that our initial state will be exactly as in the case of the impulse. So our initial state psi. Sorry, my writing is degenerating again. Psi is exactly the same initial state as in the impulse. We'll have two particles in a wave packet so that they have reasonably well-defined positions and momenta. There will be an impact parameter separating the two particles in the past, e to the IB P1, and then two plane wave states. So exactly as before. So the picture is exactly like this. So we have these two particles coming in, interacting with one another, and then, so some gravitational radiation is generated. Most of it is going to be generated, of course, when the particles are close together. That's when they accelerate most. So the waveform in scattering is going to look something like this. There's some h, there's some time, and there'll be some sort of bump, right, when the particles get close together. Okay, so how are we going to go and compute that? And I'm going to measure this waveform in the far future. Or measure this curvature in the far future, this curvature expectation. So the observable of interest is, so we need psi s dagger, so that's the future state, or mu nu, rho sigma, s psi. That's the quantity we care about. Okay, now let's write out what this thing looks like. So there's psi's and s daggers. So the Riemann tensor is, well, there's a factor minus kappa over 2. So the kappa is coming about because I'm going to work in linearized gravity. G mu nu is eta mu nu plus kappa h mu nu. So The Riemann tensor will have a kappa. There's a factor of 2, which comes about because there's a 2 in the Christoffel, in the gammas, the Christoffel symbols. Other than that, this Riemann tensor looks like derivatives, d mu, d rho, of some perturbative metric field operator, u sigma, plus various terms that have different index orderings, you know, d rhos, d mu's, various things. So index perms, S psi. Okay, now in writing this, I'm throwing away terms that have h squares, h cubes, h to the fourths, right? And the reason for that is, well, this expectation value of h has a fall off 1 over distance, right? It's easy to show this. I'm not going to do it. It's not so hard to do it. There's a stationary phase argument that shows that there's a 1 over r here for each r. So expectation values of h squared, well, let's write it like this, go like 1 over r squared. So what this is saying is, you know, in a situation where you're interested in a waveform which was generated very, very far away, as in the case of LIGO, well, then we're just going to ignore terms that have 2 powers of h. You know, that 1 over r squared is 1 over an astronomical distance squared, so it's really just 0. So we get to drop all of the nonlinear terms in the Riemann tensor, right, at the point of observation. This is exactly what people do in the theory of LIGO. This is not to say that there isn't nonlinearities in the waveform. There are nonlinearities. They're generated when the particles are close together. And those we keep. So there's going to be a perturbative expansion of this thing, but we just get to throw away squares of it. Okay. So that means that essentially what I'm really measuring is an expectation value of the linearized Riemann tensor, and that's gauge invariant in the linear theory. Okay. Very good. Now, so what about this field operator? What is it like? So the field operator so we can mode expand it. So h mu nu of x. So now field operators always involve an integral over on-shell momentum space. So this is just that on-shell momentum space integral again. There's a term with the polarization. I should really have a sum over helicities here. Polarization vectors. There's an annihilation operator for a graviton of momentum k, and e to the minus I k dot x. And then another term which is just the Hermitian conjugate. So that's the Riemann tensor operator. And here I've fed in that I know that I can always take the polarization tensor to be an outer product of 2 polarization vectors. So then, this observable here, psi s dagger Riemann tensor, equals, okay, so the minus sign is going to go away, which is why I put it in. Minus sign goes away when I differentiate this thing twice and bring down to various factors of minus I. Yeah, that sounds like it'll go away. Good. So there's a kappa over 2, sum over helicities, integral over on-shell phase space, 2 powers of epsilon. These d's now will just become k's, right? So the derivative brings down a factor of k. So you're going to get a k mu, and then it's easy to get the index perms right. No, well, I say that. Epsilon mu, k rho, epsilon sigma. Good. E to the minus I k dot x. And then there's the sort of non-trivial stuff, which has our state, S matrix. So an expectation value of this annihilation operator, basically. So here, these square brackets are anti-symmetrization symbols with no factor of 2, right? So maybe it's worth writing. K mu epsilon u minus K nu epsilon mu. Okay, so that's our Riemann tensor operator. Now, the main quantity, the quantity you have to determine here is this expectation value. Everything else, it's just, pretty trivial stuff, right? So the quantity of interest, the key quantity, is this thing. I'm going to give it a name, alpha h of k. So this expectation psi s dagger ah of k s psi. So I call this the wave shape, right? Well, there's some reason for that. One can connect this wave shape to the coherent state, to some sort of coherent state. It has some other existence. The name really comes from that other existence. But from here, the real point about it is that once you know this alpha and you shove it in this formula, well, then you get the wave. You get the actual, you get the expectation value of this Riemann tensor. Okay, so this is the basic object that we need to compute to get an understanding of what the gravitational waveform is going to look like. So our first job then is to go ahead and expand what it's like in perturbation theory. So today I'll just talk about the leading order term. I may manage to squeeze in a discussion of the next to leading order term in the next lecture tomorrow, or in my next lecture tomorrow. So we'll see how that goes, but I'll certainly talk about the leading order case. Now, at leading order, what that means is, of these S matrices, I'm not going to consider terms that have T dagger T. Right? It's very like the impulse I talked about just a little while ago, where I had 2 T daggers. That was a one loop thing. So at one loop, there will be 2 T daggers. At leading order, I just have to grab 1 T out of these S's. Right? So now, if I replace this S here, so if I put the 1 for this S, right? Yeah, I'll keep that one. If I put a 1 in here, well, then that annihilation operator goes ahead and acts on my state. And the state has 2 massive particles. It doesn't have any gravitons in it, right? So the annihilation operator is going to come along and find that there's a vacuum, graviton vacuum in here, so it's going to kill it. So that term is 0. So the only terms that you care about then are terms where there is a T in here. There always has to be a T. So at leading order, then I get to replace this S by unity and just keep the T in there. So at leading order, alpha h of k is psi ah of k I transition psi. All right, so, well, to simplify this now, the next obvious step is to put in the state. We'll perform manipulations on the state which are incredibly analogous to the manipulations I did in the case of the impulse, so I'll be brief about it. The definition of the initial state. And we will get alpha h of k is, okay, so there'll be a phase space integral, p1 prime, p2 prime, p1, p2. We have our wave packets for our initial and final states, e to the I b dot p minus p1 prime. I'm just going to ignore h bars now. We talked about those ad nauseum. So I'm sure you don't want to hear me mention the word h bar ever again. And I certainly don't want to say it ever again. Times p1 prime, p2 prime. Now, this annihilation operator acts in its conjugate here to generate a graviton of a helicity h times t, p1, p2, and I guess there's an I running around the place. All right, so in the classical region, I'll set up some kinematics for myself. So Hang on, let me try and be consistent and draw the process going up the board. So P1, P2, I'll say that outgoing particles have momentum P plus Q, and there's a K coming out there. Right? So K plus Q1 plus Q2 better be 0 by momentum conservation. In these phase-space integrals, I'll shift the P primes to Pi plus Qi. And then these integrals will become I times an integral. We'll have an integral over Q1, an integral over Q2. On shell conditions, I should really have angle brackets. So I'm going to write these as 2pi dot Qi. One should be careful about cancellation of these classically singular terms. That's not going to be a problem at tree level. So this wave function expectation value, I'll shove it into those double expectation values. E to the I b dot Q1, the minus sign, times 5-point amplitude. P1, P2 goes to, well, let's say P1, P2 prime K. And then there's the momentum conserving delta function, K plus Q1 plus Q2. Okay, so you see that indeed at leading order, the gravitational waveform is computed by a 5-point tree. Now, you won't be surprised to hear that in higher orders there are 5-point loops. From these terms, from T-Dagger T-type terms, there are also cuts of loops. So it's always the case that you can extract the gravitational waveform in the scattering event by studying loop level 5-point amplitudes. Right? You don't need any higher amplitudes. Good. So our job then, well, maybe I should pause. I mean, this could be a good point for questions. If anybody has any. Yep. No, it's just because there's two quantities that we're expanding in basically. One quantity is g Newton if you want. The other quantity is 1 over distance. Right? So I'm always throwing away 1 over distance squared. With LIGO physics in mind, right? I mean, with LIGO physics, those black hole pairs are really, really very far, very far away. So if you square this, you get 0. You square that distance, you get nothing. And it's the same here. So that's the idea. So I'm throwing away terms in the Riemann tensor operator, which are a higher order in H. But I'm keeping perturbations, the perturbative structure of H itself. So H itself has a complicated nonlinear structure. I'm just throwing away this thing that's H squared. Any other questions? Oh, yep. Sorry. Yeah, that's right. But there are no components that survive. Yeah, I mean, let me see. Am I understanding your question right? So LIGO is, the LIGO detector measures the linearized Riemann tensor because it's very, very far away from the source and the nonlinear terms are negligible. It measures specific components of the linearized Riemann tensor. The specific components that LIGO measures are, it's always going to be two time components. And then there are two spatial directions. The spatial directions that LIGO actually measure are related to the shape of the LIGO detector itself. It's called an antenna pattern. Basically, it's picking out some polarization that it's particularly sensitive to, maximally sensitive to. Any other questions? Okay, so, since we see that we care about 5-point trees, let's go ahead and start trying to understand computing 5-point trees. So I'll stick here to 5 points. Now let's see. Yeah. Okay. Now, so the situation of interest looks like this. So there's some blob here with some outgoing guys. P1, P1 plus Q1, P2 plus Q2, and some momentum K. So I want to compute this 5.3. One way to do it in gravity is by the double copy. So a first thing to study is the 5.3 in the single copy theory. Now the easiest computation by far is the 5-point amplitude in E and M, QED basically, or in scalar QED. So that obviously doesn't compute directly a Riemann tensor, but it computes a very similar object, a field strength, the expectation of a field strength in electrodynamics. So rather than measuring a Riemann tensor, I would just put in an F mu nu. Everything goes through exactly analogously. The expectation value of the F mu nu, so the amount of light generated when two charges scatter, is given by a 5.3 in E and M. So let's go ahead and compute it. It's a nice calculation. We'll start with the E and M. Okay, so we can perform the computation with generalized unitarity. So basically, we can fuse together two lower point trees. So then what we'll need to worry about are diagrams like this. So a 3-point amplitude and a 4-point amplitude. And there's another diagram which look like this. So and you can literally add these in E and M. So if this is particle 1, this is particle 2. This term here involves a Compton amplitude of particle 1 and a 3-point amplitude of particle 2. So it is order Q1 squared, Q2. This one, on the other hand, is order Q1, Q2 squared. So they're in different charge sectors of the theory, which means that these two objects are separately gauge invariant, and you could just go ahead and compute one. Compute one of these cuts. The other one, the second cut, which you'll just add, is obtained by symmetrizing over 1 and 2. Right. So let's just compute this one. Let's work in the Q1 squared, Q2 charge sector. This is essentially a kind of color ordering. It's an electrodynamics version of color ordering. Okay, so so life is very good because we get to use the same sort of ideas as in the last lecture, which is, if I'm snipping that leg off, the upper blob is a Compton blob. So, so the cut is, well, I guess it's I times cut. Okay, so there'll be a sum over helicities. So over helicities, the upper Compton has a 2i, I guess an e squared, q1 squared. I need some notation. So let's see, so there's momentum k coming out. That is p2 plus q2. So I guess there's a momentum q2 crossing that cut. And the polarization vectors, which I can put in, well, let's see. So for my Compton, I have an outgoing polarization vector, momentum k. It's dotted into, in that diagram, it's also an outgoing polarization vector of momentum q2. I mean, these stars are really a big deal. I'm sort of putting them in to be slightly pedantic, but I wouldn't worry about them at all. And then at the bottom 3-point amplitude, I have there's a factor 2i e q2, and the momentum P2 dotted with, now it's an incoming, epsilon of Q2. Okay, so the only helicity sum to worry about is this one here. Now I will use the projector. So I will use recall from the exercise, which I'm assuming that you've already done over lunch. Busy people. Sum over helicities, epsilon star mu epsilon nu equal. Okay, so I guess our, yeah. Okay, so there's a minus eta mu nu, maybe. Plus or a minus eta mu nu. Yeah. Plus, okay, so I'm interested in photons of momentum K2. And I'm in the gauge, I set, yeah, so to use this simplified form of the Compton amplitude, I have to choose the gauge P1 dot epsilon equals 0 for every polarization vector at the Compton. So these two guys are in gauge P1, so others will be a Q2 mu, P1 nu, Q2 mu, P1 mu over P1 dot Q2 minus M1 squared sorry, this is Q2 mu, Q2 nu over P1 dot Q2 squared. Okay. Now, it's very helpful, well, probably very helpful that I'm dotting in here. You know, so I have to take this projector, shove it in for these two epsilons, and then dot in with the P2. So if I dot this in with P2, well, the P2 will hit this eta mu nu. Let me give this a name. I'll call it the projector. Sorry. Yeah, okay, I think the overall sign is correct. One way to worry about the overall sign is if I dot this thing in with another epsilon, an epsilon mu, well, I should get epsilon mu, epsilon u. So I'm dotting in with epsilon upper mu. Well, that should hit this thing, give me a minus sign because epsilon to epsilon star is -1, and leave this epsilon u. So dotting in with an epsilon, well, it'll hit this term. There's that minus sign I want, so the overall sign is right. And everything else is just going to be 0 by the gauge choices. Okay, so very good. So note P2 mu, P mu nu. So this P2, now I'm dotting it in, is going to be minus P2 index nu. Now, P2 dot Q2 equals 0. That's the, these delta functions here. P2 dot Q2 equals 0. I don't have to worry about any classically singular stuff here. There's no super classical, it's just 0. So I just set P2 dot Q2 to 0, so that term doesn't contribute. This term also drops out completely, which is nice. And there's just one other term, plus P1 dot P2 over P1 dot Q2, Q2 nu. Okay, so so this thing just ends up dotted with epsilon of k, and your cut is equal to there's some minus sign there, minus e cubed q1 squared q2 is a factor of 4. Okay, so let's flip that sign. P2 dot epsilon of k star minus P1 dot P2 over P1 dot Q2 Q2 dot epsilon star. Okay, and that's basically that. The amplitude is going to be basically that cut times the photon propagator, which I didn't put in. This proton propagator 1 over Q2 squared. Yeah. Okay. So amp. Well. over Q2 squared, and then this P2 dot epsilon star. Q2 dot epsilon star. Okay, so if you put this thing, this amplitude in here, well, there's some, you can integrate out one of the Q's with this delta function, then you just have a Fourier transform to do, and that will give you the analog of the waveform in E and M. Okay, well, what about going to gravity? Well, in gravity, you can perform a very simple, similar computation. There's still two cuts. The cuts themselves will involve the photon or the graviton 3-point amplitude and the graviton Compton amplitude. The graviton Compton amplitude is something I was going to talk a little bit more about in the exercises later, but it's something that is, we can obtain from the double copy, KLT style double copy. So you can know both of these things, but there is a bit of a tricky business in that in gravity, these two cuts are not independent, so they're related. I mean, you don't have some charges which you can vary to make them completely independent. The mass counting turns out to be the same between them, so you just have to compute them together. And you have to be very careful because there are certain channels in common between both. So you don't get to just add. You need to merge them to get the correct answer. So it's a slightly more tricky procedure. You need to make an ansatz, basically, and then constrain the ansatz with the cuts. I don't know if Zvi might have talked about that in his lectures. Okay, so in view of that, there's another way we can do the computation, which is using the double copy, the BCJ form of the double copy. So let me say a few words about that, and then maybe I'll hand over to Radu. So we can get the gravity amplitude from Yang-Mills via BCJ. So in Yang-Mills, there's so the first job then is to construct the Yang-Mills amplitude. Sorry, I'm now in a different convention. So in Yang-Mills, there's a set of diagrams to compute. So there's this diagram, diagram A. So these are cubic diagrams, the kind of cubic topologies that you need to worry about when you're doing a computation using BCJ double copy. And there's these two. Okay, so let's call them A, B, C, D, and E. So 5 diagrams that one needs to compute. Okay, so in Yang-Mills theory, these diagrams are going to come with color factors. So and this is particle 1, this is particle 2. The color factor of NA, of diagram A, will have a T. So this is a free index, T1A, T1B. So that is a matrix product, a matrix product along this line. There is a shared index by this gluon propagator across to line 2, T2B. CB, well here the index A is in a different position relative to this vertex here. So there'll be a T1B, matrix product T1A, and then a T2B, just summed on the B. And diagram C, these are C's, has a color factor. Well, this one has T1A. Then there's an FABC here. Now, that's not a B and A then, so I want to keep that as a dangling index. Let's say this is, well, I probably want to say this is B and that's C. So let's write it out like this. So there'll be an FABC, T2, B, T1C. Okay, and then similarly for diagrams D and E. Right? So, well, why am I telling you this? It's because there is a Jacobi relation amongst these. So notice that CA minus CB involves a commutator of these things, of the t's, t1a, t1b, commutator with the t2b running around the place, and this is an I, FABC, T1C, T2B. So that seems to be equal to, well, my conventions are messing me up with this I, which I probably don't want to have in these conventions, but anyway, the point is that there's a relation to CC. So one needs to have numerators that satisfy color kinematics duality. There's a genuine constraint from color kinematics duality here. Okay, so I'm not going to go through the computation in great detail. It's something you can do. It's a bit of work. It's not a huge amount of work. So it's straightforward to construct the numerators. These numerators NA, NB, NC, ND, and NE. Again, you can just construct them from Feynman diagrams directly from the Lagrangian. It's, yeah, the only, these diagrams, A, B, D, and E, are basically diagrams in electrodynamics, so they're super easy to compute with Feynman diagrams. This one has one gluon three-point vertex. It is not very difficult to compute it, maybe a couple of terms. You have to worry about the four-point diagrams and correctly associate them with these diagrams, with the various diagrams that four-point vertices can contribute to. But if you do that, you'll find out of the box that color kinematics duality is just automatically satisfied. I don't know what, didn't have to be like that, but it just happens to be that that's what happens. So it's automatically satisfied, which means that the double copy just goes through in a straightforward way. So you get to write M is the sum over the squared diagrams over the same propagator denominators, and that gives you a 5-point amplitude, which you can go ahead and put directly into this formula here to get a gravitational waveform. It's not the gravitational waveform in gravity, though, pure Einstein gravity. There's a dilaton. So to remove the dilaton, you can go through a story analogous to the one I discussed for 4-point amplitudes. That's one easy way to get rid of the dilaton protrusion. So you just look at the factorization channel, and when you see that the factorization channel isn't what it should be for gravitons, you go and you put in the minus term. That'll kill the dilaton. And when you've done that, you really do have the right amplitude to put in here, and you can then do the integrals and get the leading order waveform. The waveform you get was computed first by Kovacs and Thorne, a waveform in scattering. Okay, so yeah, so that's what I thought I'd talk about now. Is there any questions about that? Yes. Yeah. In Feynman gauge. Yeah, I mean, there's, you'd think, well, I mean, color kinematics duality isn't something that necessarily has to be satisfied by Feynman diagrams. You might have to do some generalized gauge transformation to get the numerators into color kinematics dual form. You might expect that's a job you have to do. There are exceptions. So at 4 points in pure Yang-Mills, it just works. This is just as simple. Well, it's maybe slightly more complicated, more diagrams, but it's almost just as simple, which is fantastic. Why that is, I don't know. Okay, sounds maybe like that's it for me.
Now for the second part of this lecture, we have Radu again.
Hello? Yeah, all right. Great, so last thing we talked about this morning was the constraints that we would like to impose on the construction of loop amplitudes so that we restrict ourselves to the pieces of the loop amplitudes that we care for when we are taking the classical limit. So constraints. So we had several constraints. One was that each loop has at least one matter line. The second constraint was that no gravitons or messengers start and end on the same matter line. And we also have no intersecting matter lines. So the plan for the next, say, 5 minutes or so is to use these constraints and construct directly the piece of the one loop amplitude two scalars goes to two scalars in QED and GR. And this is closely related to what you've seen last week in Zvi's lectures. And also it's closely related to what Donal talked about in the morning. It more or less starts where Donal ended and goes backwards, at least for a little while. So how are we going to do it? We're going to do this using generalized unitarity. So, as you discussed last week, generalized unitarity instructs you to first draw all the generalized cuts that could potentially determine pieces of this amplitude, which sort of looks like this. So two things go in, two things go out. And I'm going to take all of them to go out just for to make my life easy as far as signs are concerned. So generalized unitarity instructs us to draw all the cuts that could potentially contribute to this and then merge them in some way. So let's see. For this, for a 2 to 2 one loop amplitude, we have two kinds of cuts. This one, so this is 1, 2, 3, 4. And these lines are cut. And then there is another one. And in here, these are matter lines that are cut. And here it's messengers that are cut. So I'm sure Zvi last week discussed these and merged them and found some relatively long and unwieldy expression. So we are going to take that, we're going to revisit that merging and get a much smaller expression, the one, only the part that we care for. All right, so to that end, let's start from the end and think a little bit about whether we should care about this cut at all. So the fact that we cut these propagators here means that we are forcing these lines to be present. And the fact that we don't say anything about the stuff that goes on in here, it means that even though there is a messenger buried in there, that messenger can be collapsed. And in here, there could be some trees that look like this, but there could also be trees that look like this, or trees that look like this. This one, strictly speaking, doesn't occur because these have different masses and we didn't put anything like that in our Lagrangian. But this one could, in principle, occur. And not because it's in the Lagrangian, but because there are momenta in vertices and they collapse this propagator. This said, we really don't care about graphs like this, because if we kept them, then that would violate our third restriction. Therefore, we somehow want to forbid these guys. How do we forbid these guys? Well, if these guys aren't there, it means that there is a messenger there. It means that we can cut the messenger. But if we cut the messenger that's buried in this blob, then we are basically back up here. So the conclusion is that the graphs captured by this cut and not by the cut number 1 have intersecting matter lines. Therefore, we don't care about them. Therefore, we can, for our purpose, ignore the second cut and declare that for our purpose, and I emphasize that for our purpose, the amplitude that we care for, one loop 2 to 2, is in fact equal to this cut. And these lines are cut. Any questions? Yes.
There's two separate arguments. One is that there's no vertex for the first cut.
Yes.
The second one, though, goes back to the previous thing about not having the rectangle.
That's right. So this kind of integrals. So both Donal and I mentioned this in two different ways. My counting of this was what would an integral of this type depend on? Right. So it can depend on masses. It can depend on what momentum invariance. This momentum squares to a mass. This momentum squares to P1 dot P2. This plus this squares to a mass. There is no Q. And because of so there is no Q that comes from the integrand. There is no Q that comes from the integral. Therefore, this graph is not something that we care for because it cannot possibly produce the 1 over Q that we are searching for. Yep. Yeah. That's right. So if you remember, we discussed, I guess Monday or maybe Tuesday. So we looked at the 2 to 2 scalar scattering in QED, and we found that it looks like this: 1 over Q square. There was, I guess, a 2, P1 dot P2. So this is 1 and 2, plus a Q square. Right? So we call this a Darwin term upon Fourier transform and so on. So it's this guy, right? So this guy collapses the propagator, and it gives this. It so appears because, well, there are momenta here, there are momenta there. The propagator has an eta mu nu, and it contracts those momenta. So they just organize themselves into this form. More questions? All right. So to construct this, clearly we need 2 copies of the Compton amplitude, either in QED or in GR. So we are going to, well, you should feel free to use Donald's version. You should also feel free to use the version that I'm going to write for you. And I'm going to actually write 2 expressions. And one of your exercises will be to check that the 2 are equivalent, which you should be able to do by eye, and also to check gauge invariance of those 2, and perhaps notice why one is better than the other. All right, so the Compton amplitude with labeling, this is 1, this is 2, this is Q1, this is Q2. So this is P1, P2. So this is M Compton equals 2I Q square epsilon 1 dot P1, epsilon 2 dot P4, oops, this is 4. Why am I calling it 4 is because there's a 4 out there. Divided by P1.Q1 plus epsilon 1.P4 epsilon 2.P1 divided by P1.Q2. And I'm sure you can notice the graphs that contribute to this, plus epsilon 1.epsilon 2. So Donald's expression was just this. These two terms correspond, of course, to the exchange graphs. So this is one version of this. Another version of it is the following. It's minus epsilon 1 dotted into P4 plus Q2, epsilon 2 dotted into P4, divided by P1.Q2, P1.Q1, plus minus epsilon 1.P4, epsilon 2.P4 plus Q1, divided by P1 Q2, plus epsilon 1.epsilon 2. All right. So both of these are perfectly valid expressions for the Compton amplitude, and I'm sure you've already answered the first part of the exercise. Why are they equivalent? Right. So it's the difference is right there. And if I put the parentheses in the right place, then it will be even more clear. So the other part of the exercise will be to check their gauge invariance, meaning that M as epsilon I goes to Qi is 0. So this is exercise. And then the third part of the exercise is will be to notice why this one is better than that one. All right, anyhow, so leaving the exercise aside, we have these, and I'm going to use this one. And then we have to sew two of these into this expression. And again, we can, just as Donal was emphasizing in the morning, we can keep enforcing the on-shell condition for these two legs, because if we don't enforce the on-shell condition, then we are only going to gain terms that are proportional to L square or L minus Q square, and they will collapse these propagators, and they will give us back integrals of this type so we can throw them away. So we might as well just enforce the on-shell condition all the time, and with that in mind, we can use the following sum over states, which will be different from the one that Donal wrote. And this is the following. Maybe I should call this L because it's going to be a loop momentum here. L mu n mu plus L mu n mu divided by L dot n. So here n is some arbitrary reference vector, which is also null. So with this relation, you can, have you seen this before? Yes, no, maybe? All right, good. I saw at least 50% saying yes, so if there are questions, I'm happy to answer them during the exercise. Right, so take two of these, one for this, one for that. Take two of these, one for the top, one for the bottom, multiply them, use this, and then shake the result, and the result is then the resulting amplitude is going to look relatively nice. But before, I'm not going to do the shaking for you because, well, it requires a little bit of enterprise. But there is one thing that's worth pointing out, and that is that even though this term looks really bizarre with a reference vector and so on, if you choose the second version of the Compton amplitude, then this term is going to drop out instantly. Just put it in there, do the multiplication, it's going to drop out. If you pick the first one, then you're going to have to work for your result. You're going to have to work to get these spurious denominators to go away. So having said this, the result, the resulting one loop, 2 to 2 QED will look as follows. So these are just names for the time being. The other one. All right. So why the extra words definitely quantum and not something else will be clear in a second. But the terms that go in there, they are the terms that would be captured by this cut that we ignored, and also there would be terms captured by this cut, but in which both matter propagators are collapsed. For example, terms that come from multiplying this, one of these from one compton with the same thing from the other compton. All right, so what is IB? IB is this integral, scalar integral. Cuts don't really matter here. Then this one is this integral. Again, with these cuts. This integral is, as the picture suggests, this triangle integral. And then this one is the other one. Right. Notice that unlike Donal's expressions, Donal's integrals, I don't yet have anything cut here on the matter lines. The only things that I have cut here or on shell are the messengers, and that is inherited from the only cut that went into this calculation. So these are the integrals, the coefficients. The coefficients are as follows. CB is the same as CXB. This is a Q. And it is some constant times m1 square, m2 square, y square. So if you remember, y is p1.p2 over m1, m2. And C is for Q1, Q2 square. So these are the two coefficients of box integrals. And then C triangle is minus a half C m1 square. It's the same C as here. Let me make it that it stands out a little more. And then the other triangle all right. So any questions? All right, so now we could attempt to massage these integrals a little bit. But before that, let's worry about the corresponding calculation in gravity, because we want to do the massaging only once. So I'm going to leave space here for the corresponding coefficients in GR. So we fill in the blanks in a little bit. So we can say for GR, coupled to scalars, we can say exactly the same words that we said for QED, namely that we can start from this, from these two cuts and rule out contributions from this one and stick only to contributions from this. So we will need the gravitational Compton amplitude. And as Donal promised, we're going to talk a little bit more about this in the exercise session. But since I need a Compton amplitude, I will tell you what we're going to do with it. It follows from the KLT relation. And it's one of the very many forms of the KLT relations, I might add. But it is one that makes use only of the Compton amplitude in QED, while nominally we would need Compton amplitude in Yang-Mills theory. So it's the following. A GR equals minus 4 pi g, and then there is P1.Q2. I guess I call this Q1 and Q2. P1.Q1, P1.Q2 divided by Q1.Q2. And then there is M Compton in QED 1 Q1 Q2 4 square. Okay. So we are going to use this. And if you use it, and again, you go through the same story as before, and if you decide to use, again, the second form of the QED Compton amplitude, the sewing part is going to be trivial, or maybe I should say easier than it would be otherwise. Now, you still need to worry a little bit about the sum over states when you have gravitons instead of vectors. So this is epsilon star mu nu of Q of L, epsilon rho sigma of L. So if you use this is the same epsilon, should be the same font. So if you use the fact that asymptotic states double copy for graviton, and you decide to use 2 copies of this, then there is a slight mistake that you're making, because you're not projecting out the dilaton and the axion. So this is really, at this step is where we make the difference between GR and pretty much any other theory that contains gravity and other fields. So if you literally sum only over the states of a graviton, then this is going to look as follows. Going to look as follows. 1/2. Let me give this thing a name. Where P stands for projector. So it's P mu rho P nu sigma plus 1/2 P mu sigma P nu rho minus 1 over D minus 2 P mu nu P rho sigma. So if you ignore the last bit, this part is exactly what you might expect if you used two copies of that projector. The reason there are 2 terms here is just to enforce the symmetry in the indices mu nu and rho sigma. The removal of the dilaton and axion is done by the 3rd term. Right, having said this, this guy is a little funny. It has both the eta mu nu and this reference vector guy. But if you use the second version of the Compton amplitude, then this collapses a little bit. Right. So none of the reference vectors remain important, again, because whenever this guy gets contracted with the Compton amplitude, it dies because of gauge invariance. So this is as if you used these three level Compton amplitudes as Feynman vertices, and you connected them with, say, the Donder gauge graviton propagators. So long story short, take 2 of those, feed them through this, and do the algebra. The result is remarkably similar to the one in QED, except, of course, it's going to be slightly, it will account for the fact that GR has 2 momenta per vertex, whereas QED has 1 momentum per vertex, so there should be more Y's in here, and there are. So this is some constant, which I'm going to tell you in a second what it is. It's CGR times 4m1 square, m2 square, and then there is 2y square minus 1 square. And this guy is the same CGR times minus 3 m1 square, 5y square minus 1, and same CGR minus 3 m2 square, 5y square minus 1. Okay, and CGR equals what? CGR is 64 pi square g square and m1 square m2 square. All right. Any questions? This is just a whole bunch of algebra which you can largely teach Mathematica to do for you. Right. The thing to notice, though, perhaps the thing to notice is that this term here, this one, and similarly this one, they are related to the corresponding 3 amplitudes in GR or in QED. So in QED, the 3 amplitude was proportional to y, and in GR was proportional to 2y square minus 1. So this thing here is GR3 square, and so is this one, or at least related to QED3. And this observation is going to be extremely useful in a little bit. And to a large extent, it is also behind the cancellation that Donal exposed in the morning between the cut part of the KMOC formula and the virtual part of that formula. All right, so having said this, and now that we have these amplitudes handy, we can proceed and attempt to evaluate them, to evaluate at least part of these integrals, and then proceed to construct the radial action and the Hamiltonian. So given that I have about 7 minutes left, let's worry first about the evaluation of these integrals. What can I erase? I'm going to keep these just in case you will want to do the exercise and you did not take notes. Right, so let's talk a little bit about, oops, wrong file. Yeah, let's talk a little bit about the box parts. Right, so in Donal's calculation, the boxes morally went away, mostly, and pretty much, the meat of the result was buried inside the triangles. So let's try to analyze the boxes a little bit, shake them into some form, and tomorrow we are going to see that for us they will also go away when we are trying to construct the Hamiltonian and the radial action. So how do we proceed? we proceed based on the observation that the coefficient of the box and the coefficient of the cross box are in fact the same. Right? They're both equal to something. It doesn't exactly matter what they are at the moment. But what matters is that the two boxes actually add up. So let's try to write down what this addition actually is. So pictorially it is this. 1, 2, 3, 4. And I'm going to label them this way. No. I'm going to orient it this way. This is 1, 2, 3, 4. And I'm going to call this one L, and the same 1, 2, 3, 4. So this is, what is this? This is an integral d dl, this is d, over 2 pi to the d. And then there are some propagators here from the messengers, 1 over L square, L minus Q square. And then there's a propagator for this guy. So this guy starts out its life as P1 plus L square minus M1 square. And then we have the top propagator here, where the first one is 1 over P2 minus L square minus M2 square minus I epsilon. There's a minus I epsilon here too. This is actually quite important, the minus I epsilon. And then here, and there is 1 over L plus P3 square minus M2 square minus I epsilon. Okay. So now we get to proceed a little bit. This bit here, we can expand the parentheses, and it starts out its life as, well, it continues its life as 2p1.l plus L square minus I epsilon. This one becomes minus 2p2.l plus L square minus I epsilon. And this one is 2p3.l plus L square minus I epsilon. So now this is the stage where I get to clarify what's the difference between definitely quantum and the rest of it. So if you think about counting powers of Q in here, you will notice relatively quickly, I hope, that this does not have a uniform Q scaling. Right? L scales like Q, Q scales like Q, the measure scales like Q to the D. But then there is this denominator here. This scales like Q, this scales like Q square. So morally, this combination of, in fact, each integral and this combination contains leading powers of Q, but also subleading powers. So this is why I was calling that definitely quantum, and this is classical plus some quantum stuff in it if we expand to high enough orders in this. So let's look at first the leading term, and also at the next to leading term. So the leading term is what? Is integral d dl over 2 pi to the d, 1 over L square, L minus Q square, 1 over 2 P1.L minus I epsilon, 1 over minus 2 P2.L minus I epsilon, plus 1 over twice P3.L minus I epsilon. So if you use momentum conservation, you will notice that this P3 in there can also be replaced by P2. And then that if you ignore the I epsilon, then this combination is in fact 0. This is exactly the same combination of propagators that we encountered in the morning and also in both lectures. So this will turn into something that's 2 pi I delta of twice P2 dot L. What does this mean? This morally means essentially the stuff that we put in the beginning, or at least the stuff that we really wanted to have in the beginning. Namely that the particles here, the intermediate particle is not exactly off shell, it's really close to on shell. And this is what this thing says, that this is close to on shell by an amount that's at least of order L square. So this thing here essentially introduces a cut here. So to leading order, this combination of box integrals is just what? It is just integral ddl over 2 pi to the d. I'm going to try to get my signs right. 2 pi I delta of twice P2 dot L divided by the remaining stuff. L square, L minus Q square, 2P1 dot L minus I epsilon. All right, so this is something that is worth keeping in mind, at least for a little while. So that little while is tomorrow until, I don't know, 10:30, give or take. You can forget it afterwards. And the reason is worth keeping that in mind is that this is going to be something that we're going to get relatively quickly from the effective field theory calculation. And we want to keep it this way because we don't want to attempt to evaluate this because one, it's not easy, it is not straightforward, and two, happens to be divergent, and we want to get rid of that. So if we can cancel things which we know are divergent without actually computing them, that, that's better. All right, so keep in mind this form. Now, keep in mind, let's try another thing here. This is IB plus I cross B is some integral stuff that includes a delta function. I'm just repeating that. And now I want to further process a little bit the remaining denominator. 1 over 2P1 dot L minus I epsilon. Right, so I can do this. Maybe I should write this overall L square minus Q square ddl. So this, again, this will be important when we construct the Hamiltonian EFT. The next step that we're going to take right now will be useful when we are going to construct the radial action. So imagine writing this as a half this stuff plus a half this stuff in which we do the change of variables. L goes to Q minus L. This is a perfectly valid change of variables. It just is a reparametrization of this integral. We choose to call L the other graviton and not this one. So what happens when we do this? The denominators change, switch places. P2 dot L goes into minus P2 dot L plus P2 dot Q. And this is plus or minus a half Q square. I forget whether it's plus or a minus. So this means that we can ignore this guy because it's subleading. So this just becomes the L over 2 pi to the D, delta L square, L minus Q square. And then the one lonely term that's linear in L now gets a friend. So there's a 1/2. Gets a friend. So 2P1 dot L minus I epsilon. So that's this guy. And its friend is this guy in P1 dot L goes into minus P1 dot L plus P1 dot Q, which is again of order Q square, plus 1 over minus twice P1 dot L minus I epsilon. The story repeats itself. We have the same nice combination of propagators, which vanishes if there's an I epsilon. So this is another 2 pi I delta of 2P1 dot L. So what have we learned out of this? That somewhere inside this combination of bubbles, inside this combination of box integrals, in fact, there is really a single thing that, that is important, and that thing really looks like this. It has two cuts. And moreover, not only that it has two cuts, but its coefficient is proportional to the 3 square, both in QED and in GR. So I guess you can see where this is going. I should stop, I guess. You can see where this is going. This is just 3 times 3 integrated over 2-particle phase space, which is something that we really loved when we were interested in the radial action. So I guess that gives you some indication where this is going, and we're going to try to fill in the details tomorrow. So I guess that's pretty much all that I wanted to say. Thanks.
Any quick questions for Radu or for Donald? Because they share the lecture now.
Sorry, this may be a little elementary, but is there a quick way to argue why the coefficients of the box and the cross box should be the same? I was trying to construct an argument using maybe Lorentz invariance, but I wasn't able to. I'm sure must be some sort of reason why they're the same coefficient.
I don't know how circular you want to be. I mean, if we didn't have the argument about the radial action before, then my answer would have been, this is just an indication that the S matrix, that the elastic S matrix is unitary, therefore it must be a phase. Therefore, a structure like this has to occur. If those coefficients are different, then the box and the cross box will never combine into this. There will be all sorts of garbage left behind. Now, since I already used the argument about the exponentiation of the elastic amplitude, I'm not entirely sure I want to use this one, because it sounds like a little too circular. But ultimately, this is the reason. The elastic S matrix is a phase, and this equality is crucial, is essential for actually having that phase appear.
That's kind of a posteriori argument, right? You do this calculation and you see that if they combine this way, then you get what you want. Is there a way of seeing that the coefficients must be the same without necessarily doing this computation and seeing it? Like
I'm not aware of an argument. Besides, this equality happens only in the classical limit. Away from the classical limit, they're just not equal.
Okay.
Further questions? Quick questions? Okay, so let's thank both of our speakers now.
Thank you.